Hi there, my friends. Here is our last lecture in this introductory series about covalent bonding in compounds. Now we're going to get just a bit more real as we take this symbolic two-dimensional Lewis structures we've been generating and turn them into three-dimensional structural formulas. Our friend G.N. Lewis gave us some basic ground rules to follow in describing the electronic structure and electron distribution of simple molecular compounds. Now, if we're given a molecular formula utilizing Lewis rules, we can figure out the distribution of electrons in bonds and lone pairs about the atomic centers. Now, we're going to use this information of Lewis structures to generate an approximation of the three-dimensional shape of the molecules utilizing the valence shell electron pair repulsion, or Vesper theory. Now let's look at the fundamental tenets of the Vesper theory. The fundamental force driving Vesper theory is that negatively charged electron pairs, whether they be in bonds or lone pairs, will adopt an arrangement around the atom that minimizes the repulsive forces and will determine the geometry of the molecule. Single, double, and triple bonds between two atoms are considered a single bonding group. The number of electron pairs or groups determines the geometry the molecule will adopt. Two electron pairs or groups about a central atom will have a linear arrangement, 180-degree angles about the central atom. Three pairs will be trigonal, 120-degree angles. Four pairs will be tetrahedral, 109.5-degree angles. Five pairs will be trigonal bipyramidal, 120 degrees and 90-degree angles. And six pairs will be octahedral, 90-degree angles. Vesper theory will allow us to adjust and modify the angles described in the preceding point just a bit. We will assume the repulsion by the lone pair is greater than the repulsion of a bonding pair of electrons. So, the Vesper theory predicts that lone pair repulsions are stronger than lone pair bonding pair repulsions, which are stronger than bonding pair repulsions. This idea gives us the ability to make fine adjustments to the bond angles in the molecule. Let's demonstrate the theory with a few examples first, and then we'll formalize the theory and put everything together in tables, which will summarize all the ideas in a form for easy memorization and reference. Now we'll look at our old friend ammonia, NH3, once more. The Lewis structure of this molecule has been done already and is straightforward. Now, for the sake of Vesper theory, we know that we want to identify three quantities. First, what is the number of atoms connected to the central atom? This determines the number of bonding groups about the central atom. In ammonia, we have three hydrogen atoms bonded to the central atom, nitrogen. Thus, we have three bonding groups. Second, what is the number of lone pairs on the central atom? From our Lewis structure, we see that we have one lone pair on the central nitrogen atom. And finally, what is the total number of electron groups, bonding groups plus lone pairs around the central nitrogen atom? In ammonia, we have 4. So looking at the theory, we will have to scatter these 4 groups into a tetrahedral arrangement about the central atom. Now, we're interested in the 3D geometry of a molecule, but without the fancy graphics and just a pencil and paper at our disposal, it's useful to have a method we can use to draw the structure on a 2D surface. One useful tactic is to draw the bonds in ways that can infer the 3D nature of the molecule on a flat 2D paper. So if we see a straight line, like the one shown, then the bond and the atoms associated with it are in the plane of the paper. And if we see a hashed line, then the bond is going into the plane of the paper, and so we infer that the atom and the bond are behind the paper. And if we see a bold wedge line, then the bond is coming out at us, out of the plane of the paper, sitting kind of above the paper. Using these drawing tools, we can now draw the tetrahedral representation of the 4 electron groups around the ammonia molecule, with the hydrogen atoms forming a pyramid shape below the nitrogen and the lone pair of electrons filling up space on top. Looking at just the arrangement of the atoms, ignoring the lone electron pair at the top, the geometry and the shape of this molecule looks like a pyramid and is called trigonal pyramidal. Our first assumption of all the bond angles in this molecule would be 109.5 degrees, and due to the symmetry, each NH bond should be equal. But one of the key abilities of Vesper theory we found out is that we can refine the geometry a bit. We know that the electron repulsion due to the lone pair of electrons on top of the nitrogen atom is stronger than the bond groups, so it takes up more space, pushing the hydrogen atoms together somewhat. So we can assume that the hydrogen-nitrogen-hydrogen bond angles are probably slightly smaller than 109.5 degrees. Now, the actual values for the bond lengths and bond angles in ammonia have been measured and are known. Each nitrogen-hydrogen bond length is equal, about 102 picometers, and the HNH bond angles are about 107 degrees, smaller than the 109.5 degrees if the extra room by the lone pair electrons is not taken into consideration. To help us a bit more in categorizing and remembering different molecular shapes, we will use what has been called the AXE method to keep track of the different geometries predicted by Vesper theory. The A in AXE represents a central atom. X represents the number of atoms bonded to A, and E represents the number of lone pairs on the central atom A. The sum of the X plus E values, the bonding groups and lone pairs, is the total electron groups, called the steric number. For our ammonia example, X equals 3 and E equals 1, and the AXE representation for this molecule is AX3E, and we now know that ammonia has a trigonal pyramidal geometric shape. It should make sense to us then that any molecule having the AX3E representation will have a trigonal pyramidal shape, just like the classic example, ammonia. So at this point, we can now generate a table expanding our repertoire of molecules and shapes. The geometry names in the table are geometries according to the atomic positions, not the electron group arrangement. And notice, there's nothing here about the diatomic molecules. There isn't really anything to say, actually, because diatomic molecules can only be linear. The next 4 tables include geometries for molecules with steric numbers 2 through 6, with various numbers of lone pairs. Now, what you see for each steric number is the AXE geometries and AXE representations of these types of molecules, the name of the molecular shape according to the atomic positions, and finally, an example molecule with a computer-generated structure. Now, also included are the example molecules' Lewis structure and any resonance structures. All the shapes for the steric number 2, 3, and 4 molecules should be shapes you can quickly identify. Steric number 5 molecules, as well as steric number 6 molecules, are usually molecules that are exceptions to the Lewis rules. We won't concern ourselves too much with these systems right now. The sharing of the electrons between 2 different atoms will not be equitable. Unless the electronegativities are identical, it's more than likely that one of the atoms will be pulling much of the available electron density to itself. Let's again use our ammonia molecule as an example. At first, we want to just look at the individual bond between 2 atoms. Observe the nitrogen-hydrogen bond. We first look at the electronegativities for each atom and identify which of the 2 atoms is most electronegative. In this case, nitrogen is the more electronegative atom. In the covalent bond between hydrogen and nitrogen, nitrogen will pull most of the electron density to itself, giving it a pseudo-negative charge, and the hydrogen will have a lost charge, so we give it a pseudo-positive charge. Notice how we denote the charge with the Greek delta, with the minus and plus symbols denoting charge as a superscript. Now, if such a disparity in the charge is present between two atoms, we call this a polar bond. We also can picture this polarity by drawing an arrow along the bond, with the point of the arrow directed at the more electronegative atom in this two-atom bond. Now, it should be obvious that unless two atoms are identical, there will always be some polarity to a bond between two atoms. Now, we'll label the polarity on each bond of our ammonia molecule. After analyzing each bond in the molecule in this way, we are now ready to look at the whole molecule. Now, assume that instead of arrows, that these arrows represent forces pushing against the central atom along the bonds. Would the central atom move if we pushed along these bonds? In the case of ammonia, given its molecular structure, yes, it would. We now can draw a big arrow representing which direction we think this central atom would move. This arrow represents the overall polarity of the molecule, with the positive end being towards the hydrogens and the point of the arrow again pointing at the more negative end of the molecule, where the nitrogen is located. This big arrow is called the overall dipole of the molecule, and its presence means the molecule is polar. In summary, a polar molecule is a molecule that has an overall dipole moment once the polarity of each bond in the molecule is considered. So it looks like ammonia is a polar molecule. Now let me state right now, just because a molecule has polar bonds does not mean the molecule overall will be polar. The example we'll consider this time is the molecule boron trifluoride, BF3. If we remember, boron tends to give us structures that don't follow the regular Lewis rules. Now, the electron structure of this molecule leads us to an ax representation of AX3, and the geometry will be trigonal planar. The fluorine atom is the most electronegative atom we have on the periodic table, so polarity of each bond is definitely towards the fluorine atoms. Again, assuming the arrows are forces, the central atom will not move in this case because the net force is zero, because the molecule is too symmetric. This molecule is nonpolar. It is safe to say that highly symmetric molecules many times will be nonpolar. Let's do one more example. Difluoromethane, Cl2F2C. The Lewis structure is shown and is an AX4 type molecule. The molecular geometry must be tetrahedral then. Now each carbon-halogen bond is polar, with the electron density favoring the halogen, but the halogen fluorine will pull harder, breaking up the symmetry of the molecule. So overall, there will be a more negative side to the molecule, towards the fluorine atoms, making this molecule a polar molecule. So why do we care about the polarity in molecular systems? Well, very soon we'll not be looking at atoms and molecules by themselves. We'll need to think about great numbers of molecules and atoms held together in a huge bulk piece of matter, in mixtures, and in chemical reactions. The polarity of a molecule means a great deal in a bulk matter context because polarity plays a major role in understanding the binding forces between multiple molecules. And it's these forces that affect the matter's physical properties in the pure state and in mixtures. Now, I'm looking forward to moving on, aren't you? Catch you later.